started.
Okay. So, good evening. Let me first formally introduce today's speaker, Dr. Aniruddha Mukhopadhyay. Dr. Aniruddha Mukhopadhyay obtained his bachelor degree in mechanical engineering from Bengal Engineering College, Shibpur, Calcutta University in 1984. Subsequently, he received his MTech and PhD degrees in mechanical engineering from IIT Kanpur in 1987 and 1992, respectively. He then joined Tata Research Development and Design Center, Pune. After a few years of service in TRDC, he moved to the University of Illinois at Urbana-Champaign, USA in 1997 as a research associate under postdoctoral fellowship. Dr. Mukhopadhyay currently works as the field chief technologist in ANSYS Incorporated, Canonsburg, Pennsylvania, USA. In his present role, he engages with ANSYS Enterprise Customer Executive on technology related to digital transformation initiative. The digital engineering technologies include model-based system engineering, open collaboration ecosystem, and machine learning-based data-driven decision tool. With decades of professional experience, he is a domain expert in multiple industry segments, focusing on improving productivity and efficiency in engineering design analysis across globally distributed teams. His current role emphasizes on development and implementing technology adoption strategy to accelerate product design and process integration, enabling continuous design change practices in aerospace, automotive, and high-tech industries. Previously, Dr. Mukhopadhyay has worked for ANSYS in various other capacities, including Technical Account Manager, Chemical and Consumer Product, Manager Advanced Technology Initiative, Principal Engineer, Director of Regional Technical Services, North America Operation, and Director of Technical Services and Business Development, Global Major Account Program. He has also served Fluent for about 8 years in various capacities, including Technical Support Engineer, Senior Engineer, and Team Leader. I first met Aniruddha when he was my roommate for 2 years in Hall 10, and subsequently we stayed in adjacent room in Newfoundland Hall for another 2 years. He was the most talented student of our batch and finally graduated as topper from the university. Other than academics, his deep interest in electronic circuit design and computer hardware during his college days has definitely played a major role in his today's success. I personally benefited a lot because of my close association with him during our entire undergraduate journey at Bengal Engineering College, Shibpur. I am extremely delighted, honored to chair this session. Now I am handing over to Aniruddha to give his lecture on the topics changing landscape of product engineering, blurring the discipline boundaries in science and technology, which is extremely relevant in today's world, wherein continuous and rapid digital transformation is going on across the industries for improving productivity, efficiency, and cost. Now, Aniruddha, let us start your presentation.
Very much, Prabhat, for this eloquent introduction. I don't know if I deserve that, but thank you. Can you share? Can you see my screen? Let me. How do I get rid of this? Pop-up?
I think you can present and it will take over us.
Can you see it?
No, not yet.
Not yet. Okay. Yeah. Can you see my screen now? Yeah, I clicked on share. It didn't. Okay, it is asking me to now select this particular window, and
Yes,
now I
it's
think
okay.
it is working. Okay. Okay. Thank you. So I'm going to give a little introduction in terms of how this digital engineering is happening around the world in different industry forums, as well as in the practicing engineers in different enterprise organizations, and what are their challenges and how those things are being improved on a regular basis. But I will start with a very brief introduction to the technology trend, particularly between the hardware and the software. And then we'll go into a particular initiative that most global organizations are focusing on, which is called virtualization. And what does it mean? How does it impact product design processes and so on? I will also in the process talk about frontiers of next generation technologies and how the description that I'm going to give, how it ultimately meets with the next generation frontier of technologies. And in doing this introduction, I'm just going to talk about these following topics, including touching upon a particular use case of electrification of automobile industry, meaning electric vehicles in particular. We'll talk about a little bit of digital twin and virtual validation initiatives around these systems. And what I'm not going to touch upon is a heavy duty topics like industrial and commercial use cases, systems engineering, model-based systems engineering, um, cybersecurity, functional safety, although each one of them play a major role in the digital transformation journey. But those are very heavy topics and will probably require much longer detailed conversation, including all the way up to cloud implementation or seal, mill, heal integration. So talking about the technology, we all know about the Moore's law and how it has really paved the way of computing in the scientific domain. And over such a long period of time, not just by Intel, but this law actually delivered its promise. Looking at that and then looking at the more recent development in the GPU, the CEO of NVIDIA, Jensen Huang, he also has a wiki page, or maybe his company has created this wiki page that tries to define a Huang's law, which says that this particular technology development is going to beat the core silicon development, but the jury is out there. Time will tell whether or not we are going to have a prolonged journey in terms of accelerated development of silicon-based hardware, or there will be some disruption in the marketplace. Why is that important? Because the partner to this hardware technology is the software technology. And this individual, Ray Kurzweil, who is currently at 87 years of age at Google, he is one of the directors in the Google DeepMind program. Before that, he was well known for some of his theses that I'm going to cover in the next slide. But he is also the person who actually crafted the speaking computer for Stephen Hawking. He is the brain behind the Google books, and he is a serial entrepreneur with more than 85 patents under his belt. And why am I quoting him? Because he made the claim that the software in the last 10 years is growing in its capacity and performance by doubling every single year, whereas its price is not growing as much because of the open source initiatives around the world. This is a very profound revelation, and it goes with the other predictions that Ray had done. Historically, Ray's predictions are about 86% accurate. And if you compare that with McKinsey or other consulting companies, he is by far the best in terms of predicting the future. So what's the deal with this hardware and software, two different schools of thoughts? What they are saying is, on one hand, the hardware acceleration is enabling larger problems to solve more accurately in reasonable amount of time. And the software improvement is saying that according to his thesis of technological singularity that he published in 2003, he made a claim that before it is 2050, in fact, he later on revised it to say that by 2035 to 2040 timeline, we will be able to create a handheld computer that will have smarter brain than human brain. And that is not a Frankenstein approach. That will be very safe, useful. Particularly, he focused on medical side of the usefulness. And that whole thesis is available online. Anybody can check it. Why, again, I'm referencing to that? Because these two observations has actually started the reform in the industry. And if you look into some of the CEOs of the world, here is one example from Caterpillar in 2015, that if we do not embark on digital transformation, then somebody else will, and we will be Uber, meaning, in US, the yellow taxi, yellow cab has been completely replaced by Uber. And that's what his point of reference is, that digital solutions, digital technologies are becoming so ubiquitous, affordable, and so on, that even a hardware machinery company like mining machinery companies, they'll have to think how they are going to do autonomous vehicle. Only problem is the pace at which this will happen is very difficult to manage. And as you can see, despite noticing what is the impending challenge in front of him, he was short-lived in his role and he was retired in 2017. As a matter of fact, around this time frame, more than 10 CEOs around the world faced the same challenge. GE, Honeywell, Airbus, Rolls-Royce, you name it. All these big companies had the same struggle. What was happening is people were getting attracted to the tremendous upside, but the pathway was not described properly. There is a story behind this. If you are familiar with the Gartner hype curve, you would know why this happened. But even if it happens, companies do tempt to attempt this type of transformation journey, and they'll land up into very confusing, difficult situation. And there are some good books, good materials available, and why that happened and how to recover from that. I'm going to avoid that part of the details, but we'll say that the compendium for that particular journey is the evolution that is happening with open source, cybersecurity, scalability of engineering software. And by software, I mean all kinds of software, right? And that actually created the paradigm shift from faster, better, cheaper product creation process. The innovation used to be coded as faster, better, cheaper 10 years ago. And now people talk about accelerate, differentiate, win market. There is a relativity involved in this process. Basically, being fast is not good enough. You have to be faster than other players in the market if you want to stand out, and so on. So software is really ruling the game these days. In fact, there are concepts like software-defined machines that are now ruling much of the innovation space. However, there is a red alert, right? And this is from last year. In last year, July 29th, the Russian Nauka module that was docking with the ISS, the International Space Station, and some software glitch caused the thrusters to remain on during the docking time. And it actually threw the attitude control of the entire ISS out of control for the NASA folks. And for 45 minutes, they were like thinking that, okay, that was the doomsday scenario for the ISS, right? Of course, there was backup plan. They could shut down the whole compute system, restart it, and take care of the bugs in some ways or the other. But it highlights one of the key elements, that software can have unintended consequences. And in fact, there is a standard available to really eliminate those possibilities. But at a time when ISS was built, the standard was not in place. So I guess some of the elements are still to be done. And in fact, right now we are engaged with NASA on this and many other topics. But one of the things that I wanted to highlight here is that the digital transformation is really causing large scale disruption. And what that means is, if you look into the budget situation in NASA, over the period of 1970 or so, meaning since the Apollo timeframe, end of Apollo timeframe, the budget has really not changed much for NASA. Whereas if you look into the cost of the Apollo program, which was about $25 billion, and in today's currency, it will be about $200 billion, which means if you want to do a mission, it is so expensive that it is almost not affordable anymore. And that's why you will see US is procrastinating and postponing next lunar mission, next Mars mission, and so on and so forth. The total amount of innovation needed to go there is not happening. Instead, they are adopting the disruption themselves by going after Starliner from Boeing and Falcon 9 from SpaceX. And then they are able to show that on a constant currency basis, they can bring down the cost from $400 million per astronaut to about $50 million per astronaut. That's not good enough. So it's not given that SpaceX technology will take us to Mars or take us to the next lunar program, but at least it's a good progress, and it gave a model on how do you do cost containment and how do we avoid accidents and failures. But that's not happening only in the government-backed initiatives. Even in the commercial space, in the automotive space, similar things are happening. In 1990s, it used to cost about 6 billion or more to really issue a new car designed to the marketplace and commercially float it into the market. They made significant improvement by the year 2000 to bring it down by as much as 67%, but that was not enough. The investors community demanded more. And again, with the loss of one CEO in Ford, now they have a new plan in place that are actually promising savings of $25 billion, right, over a particular period of time. And in that process, the journey is going from modular lean manufacturing approach to architecture overall, followed by systems engineering and model-based systems engineering and product line optimization initiatives. Now, why is this connected to the digital transformation? Because the industry leaders are actually looking into going in that direction, not just for cost saving, but also innovating at faster than usual pace. In this case, Mercedes is actually adopting or has already adopted model-based systems engineering, and along with that, they adopted virtual testing in a cascaded manner. And I will cover more on this and how this is actually, anybody can do it. It's not rocket science anymore. With lots of different technologies available in fingertips, next generation students, next generation practitioners are coming in with the new ideas of enabling this kind of technologies. Same is the story with Honda, that they want to actually do entire product creation and validation in virtual mode in computer before they will go into the CAD design or actually manufacturing processes. And if you look into BMW, they actually went further ahead and published their vision in the form of a roadmap where they said their legacy CAD practices will be transformed into the digital mode of JT-driven, JT is Java Toolkit-driven digital version, and that will interface with vendors and suppliers, PDF formats, and they will be all digital before there will be actually manufactured car on the road. So they will essentially cover all software, hardware, systems integration, virtual validation, everything, and then they will go into manufacturing. So there is one iteration through the manufacturing process and the product goes out the door. It will reduce the overall cycle time by as much as 80%. Now, we talked about the cycle time reduction, we talked about digital technologies at a very high level, but it's all contained within the development organization of an automobile company. I could tell the same story with aerospace or with high-tech industry or with healthcare industry. It's the same story. There is a development organization where there are multiple different functions that they actually collaborate, coordinate among themselves and generate the whole core idea of the design. But in terms of running the engineering organization, making the dollars work and actually make the business successful, it's a much bigger story to tell. There's a lot more people involved in the process, a lot more complex processes involved, handoffs of different information, making decisions at multi-layer level. And this is the whole motivation of how we want to digitize this organization. So there is now a concept called model-based enterprise. Model-based enterprise is a code name for actually functional modeling of all these different activities in the organization and connecting them in context through data in a digital environment, in a computer, in a set of computer program. And why and how is that? So in a model-based enterprise, you will have models, and all the aims that you see here are all models. Model-based systems engineering, application lifecycle management, model-based design, and so on and so forth. And these things are various parts of the product lifecycle, from development to manufacturing to operations and services, right? If you look into the development portion itself, you will have various different enterprise level technical tools like PLM, material resource planning, enterprise resource planning tools. And you will have domain tools like software domain, architecture domain, and different physics domains, engineering domains.
The voice is getting very feeble. Can the voice be made a bit louder by adjusting the microphone?
Let me see if this improves. I don't know. Is this any better? Hello? Hello, is this any better?
Same position.
Same position? Oh, sorry about that. And I'm in a mix. I don't know how to handle this. Sorry about that.
Anyway, maybe carry on.
Okay. Okay, sorry about that. So what is happening
Yeah,
is
it's better.
each
It's
one
better.
of these.
Carry on.
Okay, thank you. Thank you. For each of these domains, then there are hundreds of engineers in a big enterprise organization that work there, and they have their own processes, they have their own data structure, they have their own authoring tools for those, and then they are trying to all go to the cloud to optimize cost and have more collaboration going. And that idea is also demanded by these cross-domain connections that they need, which is called the digital thread. So they are basically trying to say, when you are sitting in, say, systems architecture, if you want to get an information from electrical systems or mechanical systems, how are you going to fetch that data? And there is a lot of complexity associated to that in terms of who owns the data, why should I get that data, when should I get the data, is the data recent, and those kind of ambiguity needs to be taken care of, right? So these are the different challenges that are being handled there. And the tools that are supporting these have been evolving over a whole number of decades, right? And by the way, this is not what my company does. I'm just giving the broad overview. So it's nothing to do with ANSYS. So the first level of technology that came in the digital space for managing large enterprises was by IBM. It was called Enterprise Resource Planning. It was essentially a Excel spreadsheet. You can imagine like an Excel spreadsheet for the CEOs to know how they're putting money for different activities in an enterprise organization. That's essentially what it was. And then when businesses open up to B2B context, and manufacturing was getting offloaded to second parties, third parties, and so on, and then logistics became a complicated process to handle, supply chain systems came into the being. Next stage was concurrent engineering, that the supplier is making some engineering decisions along the way, and OEMs are making some engineering decisions along the way. How are they going to collaborate, coordinate, and manage the development process? PLM came into the picture with the bill of materials, with the product data management systems, and so on. And in the last 10 years, particularly, model-based systems engineering is becoming more and more predominant with architectural focus because of the complexities of the design. Now, no mechanical product is electronics free, right? And whenever you are putting an electronics, however small it is, there is a piece of software embedded in that. So now you got software, electronics, mechanical, and chances are there are a couple of other physics because of the sensors and actuators, a couple of other physics will also be there. And this complexity can be handled only when you have a model-based systems engineering tool. That's where bulk of the effort going on right now, but this is not the end. The future is in data-driven systems, data-driven digital engineering ecosystem. And that will define model in a very computer science manner, in the sense that it will be an abstract gray box where you can go in and modify it, but otherwise it takes an input, spits an output with a certain confidence limit. And this is where most of the AI ML activities are concentrating. Some of them are benefiting from background physics, some of them are benefiting from process knowledge, and so on and so forth. But this is where the technology today is. And this whole set of platforms are actually, there is a structure of complexity and hierarchy to be managed in the enterprise environment. Now, where is all this thing going? If you look back, NASA had defined a technology readiness level, TRL, right? And that gave birth to this new technology introduction process. Anybody who is trying to introduce a new product, there is a process for that called new product introduction. And the detailed engineering that goes in making that product is called new product development. Traditionally, these are 3 steps along introducing a new product to the market. But because of the digital technologies, now people are saying, can I concurrently do these things? Pretty much like build the aircraft while flying it, right? That's not possible. So how close to that can you go? That is the question. And the idea there is that we saw all the hardware improvements, we saw all the software improvement. Why can it not be done? And the answer is yes, at least we can start an effort and we can go in that direction. And then what is happening is By unlocking the prior knowledge on the design processes and design data, and using deep learning techniques, transfer learning techniques, and graph theories, yes, there is a method to the madness that you can actually codify what you do in NTI or NPI, new technology or new product introduction steps, and you can actually make use of all the things you already knew and explore what new product can you actually do and rank them, right? And that's what delivers a process that can focus on product performance, cost, schedule, and all those things. And this is where bulk of the initiatives are going on in the R&D space from the applied research point of view. And in codified term, that is taking the systems engineering and moving it to cyber physical systems, where hardware and software are going to be concurrently developed. No more just concurrent engineering for the hardware, and no more the agile engineering for the software. Do them together. And while you are doing them together, validate the design also virtually. And not only that, create a model that will live through the asset throughout its life cycle time. There are three fundamental things that enable that: the models that embodies the physics, the process, the knowledge, the hierarchy, the relationship between models, and then the management of the process and data that embodies those models and the use of those models. Now, what does it mean in terms of product engineering? Typically, when somebody makes a product, a bulk of the cost is earmarked for final validation. To give you an example, an automotive engine consumes about 40% of overall validation cost just by this final stage of this pink triangle, right? So if we can do a lot of digital exploration in the left side that will reduce the size of this pink window, then that's a value proposition. That's what they're trying to do. In fact, all these companies that I showed earlier, they're exactly trying to recreate that. How do I reduce my validation cost? So let's review what I just talked about so far. We talked about software-defined machine. We talked about engineering domain boundaries are getting blurred, and digital development process is enabling acceleration, better quality, and better performance of products. These are enterprise-wide involvement. And at the end of the day, it's about data, physics, process, and machine learning to create new knowledge for new product. Okay, so that's the blueprint. Now, various industries, various companies are in various stages of adoption of these or utilizing of these technologies. But when you look into India, and that's where it is coming home, is that as you look back into the Atmanirbhar Bharat Abhiyan, there are 15 production link incentive programs today. And by definition, all 15 of them are mandating various levels of this digital engineering technology to be adopted. We are connected with a whole host of different applicants to these incentive programs, and we are in various stages of conversation. So I have a view of how these things are happening. What I'm going to do is to take just one of those initiatives on electric vehicle, and I'm going to quickly go through in 3 slides how exactly they are thinking through this and how they are adopting. Are there global leaders who are also working in this space? Absolutely, as I mentioned earlier. But here is what is happening. We already know how a car operates and how the IC engine works and brake systems, chassis systems, wheelbase, etc., etc. In terms of design details, it's a multi-physics problem with multiple domains, systems engineering. There are many different risk factors, safety factor, and ultimately now we are talking about various levels of autonomy, right? But in the design stage or design analysis stage, there are these core 6 programs or core 6 disciplines that are constantly interoperating. So it cannot make any part of the design just thermally safe, but structurally not safe. So you have to continuously validate that all these disciplines are concurrently taken care of. And then, of course, it is connected through the software, right? Software is driving the car for the most part. And you have to deliver on functional safety, that there should be a fail-safe arrangement for any sort of operation, any sort of untoward incidences must take care of the life, right? And that's a big challenge. It's not solved problem, but people are working on it. And the key tool to enable that capability is systems engineering. Now, when you look into the product side of story, this is analysis side of the story. When you look into the product side of the story, you can easily see that a car, particularly an electric car, will have some basic subsystems. And or some of them are hardware systems, some of them will be control systems, some of them will be pure software systems, right? And for design purposes, each one of them will have some level of metrics, and you have to deliver on those metrics, but you cannot go there independent of each other. So now you have to coordinate the activities across all these subsystems and make them work together. So here is a blueprint of doing that. And remember, I talked about the ultimate aim is to really reduce the size of the pink triangle to this little by shifting it virtually to the left, and this is orders of magnitude cheaper. And you are having better idea about the design very early on. So how are you going to do that? You're going to simulate, you're going to use physics to understand the core principles of the design, and then you can go as granular you want, or you can stay at the systems engineering level to do trade studies. And then you will have a controller, corresponding controller, and for each pair of subsystem, you'll have a plant model and a controller model that you are going to iterate upon. And you will have a subsystem integration bus who will actually take all these individual subsystems to work with each other, and the coupling that I was talking about, they will be checked here. Now, this whole thing can actually be managed as software in the loop, because now everything is virtual here, except that the plant ultimately will become the physical asset. And that's when the software that is always going to remain virtual will meet the physical asset, and then you'll actually deliver a car physically somewhere. But before you do that, this blueprint allows you to drive the car like in a game engine typically on the virtual system with all its manifestation of each individual subsystems and stuff like that. So that's what you see here. Basically, you can start with a Google map for a particular destined roadways. You can look into the car of your choice and all the subsystems that are involved in that process, and you can keep your focus on either battery performance or on overall comfort or on range or on battery life, etc., right? And all of those things, multiple engineers can actually watch out when this system is working on its own. Okay, now, is this real, or how am I going to use this? The way you are going to use this is, and this is for example purposes, let's say you have 4 subsystems that you brought in, a motor, a software to control the motor, a calibration test data, and you have the battery thermal model. And you bring them up and you create a system model that actually does the behavioral understanding. These reduced order models are coming from 3D physics, so they're generally speaking high fidelity, and there is a machine learning driven calibration process which can also enhance the fidelity level, right? At the end of the day, you are going to deploy this into that Google Path engine, like Google Map engine, etc., and you're going to simulate various scenarios that are required for certification. Like anytime you want to put a car on the road, you have to go through the certification process. And one of the requirements for electric vehicle is under various load conditions, what is going to be my estimated range? And I have to ratify for a single charge how much mileage I can get. And you can actually cover that whole test matrix all in the virtual mode. This is just one example. By no means that it is done and that's what it is. This is how this whole technology is evolving. Lots of different customers, lots of different business houses are actually trying it out in various real life scenarios, but they're not stopping there. Even the controller itself is a electronic hardware, and that electronic hardware will have a local operating system. Within that operating system, we will have a BSP, board specific packages, and different drivers and stuff. All those things also can be virtualized, and in your Linux box, you can actually simulate the whole controller stack for a target control hardware. And that technology is also available today almost exclusively in open source paradigm. These RTEMs and QEMU are the critical elements. These are open source initiatives, right? And then the vendors like the hardware HIL vendors, they are gladly operating because they're seeing that the customer will be successful and they will have a natural fit into that ecosystem. So I had a lot of other topics to cover, but I thought that I will definitely run out of time. So I'm going to abbreviate the digital twin backend story. I will start with the hype curve that I briefly mentioned earlier, and I will point you to the fact that in the 2018 map of hype curve for digital twin was at the peak of expectations. Also note the color of the dot, which essentially says that as of 2018, it was at the height of the expectations, and it will take 5 to 10 years before it will go through the trough of disillusionment all the way up to the kind of steady state of slope of enlightenment and plateau of productivity. In other words, adopted in the industry, right? So this 5 to 10 years journey from 2018 is what is going on. I can talk about a techno-commercial value proposition and challenges associated to all of that, not important. What I wanted to show you, so how is this journey happening? How are people recovering from this chasm, from this idea that we have no way to really mature it from these high expectations to high delivery, right? I will talk about one element of that as to what that challenge is, what that mismatch of expectation is. So if you do a quadrant analysis between data and model and what you expect and what's the reality, it becomes very black and white in front of us. If you just purely use data and data science, yes, you can definitely make a predictive model that will be accurate enough, but it will be accurate only to the extent it was trained for the kind of data it has seen to be trained. As a result, it will not be able to predict any disruptive change or any long-term event that it didn't have data to really predict, right? So those are the basic reasons why digital twin today, or the whole techno-economic analysis that was done around this technology, has not matured yet. On the other hand, if you look into the model, how much modeling you are doing is always a question mark. You are never satisfied with the degree of details you can get into the models. And obviously, things that you are not modeling is going to remain outside of the scope of prediction, and then you're missing out. And that is, and you know that I am Russian Nauka module docking with ISS and the corresponding challenge is an artifact of the same situation. It was modeled, it was tested and everything else, but there was blind spot that was not considered. As a result, it shows up as a big challenge. And this is real life, this happens. So how do you recover from that? You bring physics to the cover. If you can actually take the data you have and you have a baseline physics model and you create an algorithm or create a mechanism, learning process on top of the learning process that actually has a mechanism of improving its fidelity level, then you can begin to recover from that. That's exactly what we are working on right now. And we have proven this to a whole host of different customers. But the whole idea is that this is not a general purpose data science tool. This is very targeted for product performance prediction, product endurance prediction, product life predictions, and model calibration, focused on model calibration, so that the engineering value it delivers is understanding the failure points, the ultimate failure points, the inception point of the failure beginning, and so on, right? Now, these are the customers, the various type of customers that these technologies has been tested out. Much of it, again, uses standard open source tools. Some of our orchestrations are unique. We have a patent behind that orchestration. But in general, that is the area of focus that I am personally driving these days. Now, at ANSYS, we are also looking into the frontier of product engineering in terms of various different technologies. And the things that I tried to cover today by talking through, these are the 5 elements that I covered. There are a whole host of other topics that are there, ICME, healthcare initiatives, cloud-related topics. And I said some of those things I'm not going to cover today. Deepankar Chaudhary, our VP of Research and Academic Programs, is visiting IIEST on July 20th in person, and he's going to give a presentation on physics-based simulation in research and education, current practices and key initiatives. With that, I will stop here and see if you have any questions. Thank you. Am I audible?
Yes,
Yes.
sir, you are audible,
Dr.
but
Maji?
Dr. Mazi is not audible. He is unmuted.
Dr. Maji, you have to unmute yourself.
Hello,
Yes.
is it audible?
Yes.
Okay. So, how you should go? The question answer directly. Audience will ask the question. You will answer.
I can.
I think so. We should start the question answer session now.
The topic was a little bit.
Aniruddha, let me ask question from me first. I think so. The India is going on in a massive scale in the electric vehicle design, and I think so. These ANSYS is definitely they are involved in the process with some of the OEMs in India.
Yes, we are. We are involved with OEMs and even some suppliers. Yes, and definitely one of the key areas that most of you know, battery safety has come up to be priority number one before you talk about other designs. All the batteries that are coming from China is a big source of problem, right? And it's well documented, not just in India, but around the world.
And your battery is based on lithium-ion battery, or you are thinking other batteries also? Like there are some other, basically the sodium-ion batteries or some other battery. Recently, IIT Madras has developed some zinc based battery which will replace the two-wheeler, three-wheeler. That's what they're claiming.
Right. So the way we work is that we create models, and the models can come from core physics. Model can also come from performance data, right? So you make a battery, you go through the charge discharge cycles, you give us those transient data, and we can give you a very high predictive models. And there is a lot of discussions to have in that domain itself, including identified runaway conditions when the battery will go rogue. There are signatures that you can capture and analyze those. But it does not limit it to be lithium-ion battery or pure lithium batteries or zinc air, or you name any technology, including fuel cell. We are actually working very intimately with some of the other Asian forerunner premier companies in the fuel cell technologies, right? And in the automobile industry itself. So all these things, as long as there is an energy source and you are trying to create a design that will be modular, portable, safe, operating, and it will meet the requirements of the safety and certification, we can definitely build models around that and connect the systems together. And it's not us. Anybody who wants to do that today, the technology is in fingertip. Anybody can do that. That's why the pace of progress is accelerating.
I think so. This model basically that will also be applicable in our steel industries also, particularly to improve the productivity. Other things like in SMS operation and blast furnace operation. Are you working? Your NCS is working in those areas also, or you are working only the high tech area? Basically,
Every steel company in India, every steel company in Korea, a lot of in China, and there are some problems with the China, some of not legal use of our technology, but overall, everybody is using various forms of our technologies. But again, let me just put it this way. I'm not here representing ANSY's portfolio or ANSY's
No,
solutions.
that is okay. I'm
The
just
technology of
telling you
simulation, I
how
would say,
how the digital transformation is going on in India. That I would like to know. Okay, US is much
so,
advanced.
so if you remember, Professor Deepak Majumdar, Professor Indra Ghosh, and Dr. Balal, Professor Balal from IIT Bombay, they have a forum where they actually meet every 4 years and talk about the cutting edge of um, steel industry. And I'm a regular participant in that as well. There is JSW, Jindal, Tata Steel. There are a whole bunch of other different companies, including the aluminum manufacturing companies. They work together to develop common technologies that will, the main aim is not to really do ab initio physics-based model, but to understand the variabilities. Because, not the coal, not the ore, not the electricity supply, not the chemicals that you use are actually of 99% purity, right? So how do you deal with this variability in your supply chain and create a methodology that gives you predictable behavior on quality, on performance, on productivity? And then, of course, safety. That's what the current motion is.
Dr. Maji, can I say a few words, please?
Yes, sir. Yes, sir. Yes, sir.
Actually, I am overwhelmed by the lecture of Professor Mukherjee, Dr.
Yes.
Mukherjee, whatever you say. My God, the whole today, I feel that to be the CEO of a production field, one needs to be almost in the level of a Nobel laureate, the level of knowledge. Otherwise, I mean, you can ask somebody to help you out with your problems, and that help will come in the form of what Aniruddha has given the lecture today. As I said, it is mind-boggling. Now there are
Not like that. Let me tell you. Sorry to interrupt, but let me tell you one quick example. Look at the Windows Word or Windows PowerPoint. Do I know how to write the program that is Windows PowerPoint or Windows Word? No. Can I write the Word document? Absolutely yes. So that's how the software is moving forward. You can use PowerPoint and actually drive a controller. Can you believe that? You can draw a circuit in PowerPoint, and behind the scene through Visual Basic Code, you can run a controller from your PowerPoint. And you don't have to be a rocket scientist to do that. Today, that is the maturity of the technology.
yes,
So
I get it. I get it. One
not
thing,
my credit at all.
one thing. No, that's okay. But your presentation, one thing get me great pleasure in looking at your slide, enterprise landscape evolution. That slide has moved me to a great extent. That slide is sort of a summary of the whole lecture that you presented. It appears to me. But a few other things I like to say. That is, you raise the point of this Ray Kurzweil. Ray
Yes.
Kurzweil once suggested. Now, first I'll come to John von Neumann. John von Neumann was a sort of mathematician. He said, you make two computers, then correct each other. One computer will learn from the atmosphere. That information he will give to the second computer. The second computer will improve upon it and put it to the first computer. So that way it is 40, 60 years back, von Neumann formed that thing. Next I am coming to Ray Kurzweil. Ray Kurzweil said, look, a baby is born. It has got no intrinsic knowledge. But you go on feeding. By 1 year, it goes on absorbing information from the atmosphere, from its surroundings, and then it creates the knowledge base. It becomes a
Yes.
human being. So he said, I make a parallelity. I'll create a computer like a baby, and then I'll ask him to go on getting knowledge, and then it will go to such a level that it becomes singularity is achieved. that kind of thing. That's rather interesting. But I was moved. I'll stop here now. I am moved by the lecture and the depth of knowledge of Mukherjee. And I was thinking at the age of 82, I don't belong to this crowd anymore. I can only see as an observer and observe.
You are simply embarrassing me.
No, no,
You
no,
are
no.
simply embarrassing me.
Sir, he was a mechanical engineer, but he is equally good in electronics as well as computer science. That is the reason he can absorb everything.
It's very difficult to absorb. Maji,
No.
I can tell at least
I know him.
I am getting limited. Biman, I like you to say something, Biman. Biman is laughing.
No, Dada. Just to say thank you, Aniruddha. And it was an excellent lecture. I don't know much about these things, but only since you said about addressing the variability aspects for different industries, may I know in your model, like say you are building an EV model versus a steel industries model, generally what kind of confidence level and confidence interval you use in your predictability?
Okay, good, very, very good question. So it depends on the context in which you're building the model. What I mean to say is that if you're starting from the physics, you know where you are grounded. The problem then becomes variability on what you model and what you left outside of model. So let me give an example. If you're talking about a structural analysis problem, we will use a standard Young's modulus and we'll say that is what it is, right? And then we'll say this is the CAD geometry, you got it. And then we'll not ask the question, the material with which I made it, I thought that it was delivered to the spec, but let me see the material spreadsheet and you will see the material provider said my Young's modulus is plus minus 3% or plus minus 10%. There you go. All of a sudden you have an unbound variability right on the property itself. But then the tolerances, the dimensions that you made, there is plus minus 2% CAD or plus minus 1% CAD variabilities, right? So how do you take these variabilities and how these variabilities will progress as what is called the uncertainty progression, right? So there is a methodology of EQ, uncertainty quantification and propagation. So if you talk to companies that are making this gas turbine engine, a gas turbine engine is rotating at 30,000 RPM at 30,000 feet in the sky, and it has a clearance with the casing that is like 30 mil, 1,000 part of inches, 30, right? With that little margin, and you are having no accident whatsoever. How is that happening? Because they control the variability along with a controller. The controller knows how to take the signature of various runaway situations and bring it back by either controlling failure ratio or controlling altitude or controlling the excess air components. And there are some other mechanisms that are purely controller algorithmic situations that it looks into the combustion characteristics and understands that there is a problem impending and it controls it, right? So how do we manage turbulence in the midair? It's exactly those kind of algorithms. I'm sorry I gave a long answer.
No, lovely
But
answer.
No, Aniruddha, this is
Beautiful
of
answer.
paramount importance, like how to tackle variability. The whole world is like dealing with it and essentially like designing. Like yesterday, we are listening to a very interesting presentation by the Apple's Alloy Engineering Group. And just for everybody's information, like, Apple has like overall probably 1.4 billion devices in the whole world, right? So now the question is simply just consider the aluminum they're using in their cell phones. That like involves this kind of variability discussion that we are talking, and like then the question comes how much material you are going to go for sustainable investment side of the equation versus like straight from the smelters. And in today's world, I don't know like whether your model extends to that varieties or that scope, like how these direct carbon capture technologies are evolving and how you are making sure that your availability of your systems are there, things of that nature. So yeah, thank you very, very much. It was a big learning curve for me, but I got a little bit of glimpse of your expertise. Thank you. It's my pleasure.
Thank you so much.
Sir, may I ask a question?
Yes.
Sure.
So actually, sir, this is basically related to this ML thing. Basically, uh, you all of you are generation from where people were designing things and they have the in-hand knowledge of designing things and they are implementing things in a ML level. Now we are in a generation we are not in a ML. It is there everywhere, and we are not having the fortune of designing things on our own. So there is a gap is creating. So how that will create a disruption in the near future or something when you will people will be not here around us and that expertise domain knowledge will be missing and all the things will be there like baby is doing how he or she is gaining knowledge we don't know, just only we have the black box things will be there, only ML knowledge will be there. How that will
Okay, I will give a short answer in two different ways, and then I will invite Professor Vishwas to give a more elaborate, eloquent answer to that. Okay, but let me give you the first two short answers. Number one, you know, we do not use abacus for our calculations anymore, right? And do you remember the table for 17? Can you tell me 17 out by 25 how much it is without looking into any calculator? No, we don't care. But we didn't forget the art of multiplication, the science of multiplication. We can do that, right? Same thing is happening. The engineering core design science has been codified into various different standards and it has become part of software. As I mentioned earlier, software defined machine, that's what is happening. So you are actually embodying the routine repetitive knowledge into some sort of a program, then embodying that program to produce the design that you would have created by manually producing it. Like for example, the drafter that we used to use for mechanical drawing. Now you can do that in AutoCAD or similar products, Solid Edge, SolidWorks, AutoCAD, PTC Creo, so many tools, right? Did you lose how to do mechanical drawing? No, you just codified it and you have computerized it. Similarly, all the design knowledge is getting into this kind of environments, right? The other answer is the ML, the machine learning, is no panacea. Yes, there has been a lot of improvement in machine learning over the years, particularly since Google, AWS, Microsoft has started putting a lot of effort. MIT's systems engineering, MIT's ML initiatives are really, I mean, I would welcome anybody to look into Julia. Julia is the next paradigm of engineering learning. You will not need explicit design books. You will need Julia environment. And if you read about, and this is open source course in MIT, you should look into this. Chris Rokakos is the person who actually drives this. It's a brilliant technology. It is really embodying all the knowledge and delivering it in the fingertips. School kids can learn with it. There is a thing called BCI, brain computing interface. Literally, school kids are running that to understand exactly how do you do the brain waves, how do you map that to different functional nodules, and then how do you actually manipulate that or study that to understand exactly how you think. School kids are figuring that out. So it's actually going in the forward direction, not in the backward direction. There is no vacuum getting created. It's getting codified so that you can learn more. Professor Vishwas, I will welcome your philosophical answer in this question as well.
Lovely answer, beautiful answer. I enjoyed
I will answer. Can the coordinator allow me to share a screen? Just I will
Yes, sir.
show.
Please.
1 second, sir. I am giving you the. Now, sir, you can present it.
Before I do this, I will definitely, go for big hands for Aniruddha. It's a wonderful presentation together with illustration. And what to say that Aniruddha's wisdom, Aniruddha's depth, Aniruddha's understanding and illustrations. All are very well acknowledged. But I would also give some, thanks or some gratitude I would like to express for Dr. Shantanu Das. What he said is possibly very, very correct. Now, these are two paradigms, but these two paradigms come in a synergistic manner. Is the slide visible?
Yes, yes.
Yes. Yes.
Okay. So here I have just tried to show, you see, it's a part of another lecture. I mean, since this discussion came and I'm working on the computer on several other things, so I thought of sharing this. Just look at the miracles that happened during last 30 years. One is microprocessor. All of you know what is the definition of microprocessor. Second is fiber optic communication. Third is QR code. Probably with respect to Aniruddha's presentation, this is more relevant because today everywhere QR code is being used for making payments and whatnot, right? Then lithium-ion battery, we were all discussing about this. Can you imagine this was discovered, complete lithium battery was discovered in 1980. And it was basically commercialized by two companies, two Japanese companies, Sony and Asahi. And three players were there. All of you know John Good